So yeah, I don't know. It probably didn't impact any of your other courses because people probably don't give you their course website on their personal pages, but I did, and they made that transition today at noon. And it wasn't done completely, and I've been interacting with them, and they're supposed to be fixing it, but nonetheless, you cannot get to my website right now, I think, maybe, but I emailed you the lecture notes for today, and I'll email you your homework assignment tonight, the start of it, obviously. Remember, your homework quiz is not going to be due or done until next Thursday. But at any rate, all right, so now is where we're going to start seeing the payoff of what we've been doing. Today we're actually going to make contact with some functions with which you've worked before. And then on Tuesday of next week, we're actually going to skip. We're actually not going to skip, but based on the skipping of a few sections to get to the last section I told you to look at today, we're going to move right beyond that into sort of the unified picture of all of this. And so what I'm talking about is polynomial functions. So there's a uniform framework in which all the polynomial functions as a basis of Hilbert space works. And then after we've talked about this unification scenario, we'll go back and look at the non-polynomial functions, which are a good basis in Hilbert space, things like Fourier series and so forth. So at any rate, last time I had one final result that I needed to mention, but we ran out of time, so I'm going to start with it, and that is the following. If P and Z uniformly converges to some function g of z, then it also converges in the mean. Okay, this is something you should be familiar with. Okay, remember, uniform convergence is sort of the most powerful form of convergence because you just pick that number across all values of x, and you can pick epsilon, and then the number that the indices have to exceed is only going to be dependent on that epsilon value. It's not going to depend on where you are. If it depends on where you are, that is of course pointwise convergence. But uniform convergence, that number doesn't depend on where you are. Uniform convergence implies pointwise convergence, and it also implies convergence in the mean. Okay, so if you converge uniformly to the function g of z, you're also converging in the mean. Now, the reason I bring that up is the following. Any element of Hilbert space, which is the set that we are most interested in analyzing, and these can be continuous or not. Okay, so Hilbert space is just this space of square integrable functions. Many of those are continuous, but they're not all continuous. But it turns out that any element of Hilbert space can be approximated by a continuous function. Now, the proof of this actually happens way later in the book, and we're not going to mess around with the proof, okay? But it's just important to realize that even if you're dealing with a non-continuous function in Hilbert space, there is an approximation to it which is continuous. And then we have the following result, which is due to Weierstrass. And that is continuous functions can be approximated in the mean, and you might not remember this from my last meeting, by polynomial Pn sequence. Therefore, elements of Hilbert space can be approximated by what? Say it again?
Polynomial functions.
Exactly, thank you. Okay? So one way to visualize this is just to say, okay, well, if I take a function in Hilbert space phi, and I take some polynomial, and I want to know, well, does that polynomial actually approximate the function phi? Well, all we do is we introduce some continuous function f, okay? And by the triangle inequality, one thing that we know is that phi minus pn magnitude is less than or equal to the magnitude of phi minus f plus the magnitude of f minus pn, okay? And the statement that phi, the function in Hilbert space, can be approximated by f is basically the statement that this can be as small as you want. That's what an approximation does, okay? But then the statement due to Weierstrass that any continuous function can be approximated by the polynomial means that that can be as small as you want, which of course means their sum can be as small as you want. Therefore, the functions in Hilbert space, whether they're continuous or not, can be approximated by polynomials. Okay? All right. Now, if you think about this for a moment, if you think about the fact that anything in Hilbert space can be represented by a polynomial function. It might take going to infinity, but you can do it, okay? Then this seems to point towards polynomial functions as constituting a basis in the Hilbert space, right? Okay, so now what we want to do is we want to focus on this for a bit. Now notice I said the word basis, not necessarily orthonormal yet. We'll get there. Okay, so due to Weierstrass, we know that a function f can be approximated uniformly by the sequence Pn of x equals sum from m equals to 0 to n a n m x m. And this will approximate a function fx, for example. Okay? Now, obviously we could take the set, since we're in polynomial space, we could take the set x0, x1, dot, 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 up to x2n. And this set is going to be linearly independent. Okay? That should be pretty obvious. But what very, very useful property does it not hold, Joel?
It's not orthogonal.
It's not orthogonal. Excellent. Josh,
Yes.
how are we going to fix it?
Graham-Schmidt.
We're going to Graham-Schmidt the shit out of it. Exactly. Okay. Now, if we Graham-Schmidt it, which we will do explicitly in a few minutes, if we Graham-Schmidt it, then we can imagine that we're going to find these basis vectors as linear combinations of the QIs, where the QIs are orthogonal. In fact, we can normalize them so that they're orthonormal. All right? Now, QI is a function of x? What kind of function of x is it? Joe? Exponential, logarithmic, hyperbolic, modular, idempotent, polynomial, polynomial, yes, it's a yeah, look. When we Graham-Schmidt this, Graham-Schmitting is not going to radically change the form of what you're putting into it, what you're building it with. So if you're starting out with these, which are just the basis of polynomials, then the basis that's going to result from Graham-Schmitting is also going to be polynomials. Okay? These are just going to not be, x0 or constant x1. They're going to be linear combinations of those. Okay? So once we can do that, then that means that our polynomials here can be written as a linear combination of these polynomials. Okay, so polynomial gives you a polynomial. It's a nice closed story. Now, we know when we Graham-Schmidt this thing that the QIs are going to be orthonormal. I mean, that's what Graham-Schmitting does. So the only question that is left to be answered, if we want to know is this a good orthonormal basis, is whether or not that set is Madison. Madison. Oh man, I think she signed in. Oh, complete. Yeah, thank you. Thank you for the chat message. It's complete. Yes. She chatted me up. Yeah, so we got to ask whether this set of QIs is complete or not. Okay? So, here we go. If they are closed, hold on, okay, so QI are complete if they are closed. Okay? And they are closed if, how many of you remember the condition that must be satisfied in order for a set to be closed?
The couch sequence cannot tend outside the space.
Yes. There's another way to put it. There was a way that we put it in terms of orthogonality. That was definitely one way that we put it, but what was the method? I'm going to do a proof with this, so what's the other method in terms of orthogonality?
Was it the outer product one?
Mm-mm.
If the inner product of a function with bases is equal to 0, that implies necessarily that the function is 0.
If the set is complete.
Yeah.
Yes, good, good, good. Closed if f qn for an arbitrary function, not an arbitrary function, but f with all of the qn equals 0 implies that the function is 0. Okay? Now, the first thing I want you to note is if the QIs are or are not complete, then we have to have this be true. But since the QIs are just polynomials embedded into this polynomial, then this being true to demonstrate that QI is complete translates into FPN equaling 0. Okay? That's the wonderful thing about polynomials. All right, they don't really do anything that unique or different. Okay, so here's what we'll do. We know from Weierstrass that f of x can be approximated by p and x. So given an epsilon, there exists an n such that the magnitude of f minus pn is less than epsilon. Now, suppose that we have an f which is orthogonal to all of the pn's. Okay? Then, if I consider the difference, f minus pn, then this is, of course, f minus pn, f minus pn, 1/2. Okay. But when I do this inner product and exploit its linearity, I'm going to have at various points the inner product of f with pn, which is 0, okay, by assumption. So this is going to simplify to the magnitude of f squared plus the magnitude of pn squared. Okay? So we have that magnitude of f squared, sorry, to the 1/2. So we have that the magnitude of f squared plus the magnitude of pn squared has got to be less than epsilon squared. I just squared both sides of this expression. Okay? Now we can take epsilon to be as small as we want. We can dial it down to 0, which of course means that f is what? These are two positive things added together to give me a number that's less than epsilon squared. What is this going to? 0. Okay? Of course this is going to 0 too, but f is what we're concerned with. All right? So therefore, the set Pn is closed. But if the set Pn is closed, that automatically implies that the set Qn is closed. Okay? Therefore, Qn constitutes an orthonormal basis in Hilbert space. Yes?
Wait, so it's closed if the inner product of f with any q is 0, it implies that f is 0?
Yes.
But what if you do another q as f? Because aren't they supposed to be orthogonal?
Sorry, say it again?
Well, because the q's are orthogonal, right? So if you did a q, if f was equal to q that's not n, is that allowed?
Well, this is supposed to be for all n.
Oh, okay, and then you'll get one that's 1. 'Cause I'm just thinking the q's are orthonormal.
Yes.
So if you pick f to be one of the q's that is not, or just any of the q's, then you'll get 0 for some of them. But I guess not all of them.
Yeah, right. No. Okay, so you pick f. I see what you're saying, and it is confusing. So you pick f. F must be orthogonal to every qn. Now, if you want to pick f to be a q, then it's orthogonal to everything except itself. And then qn is 1. Okay? But you want it to be 0 for everything. It's kind of weird because if f is 0, it's kind of got these funny properties, which do not translate into non-zero things. So sometimes the statements we make seem a bit odd. Okay, so now just really quickly, oh, sorry, yeah, go ahead.
Is it I'm sorry, could you repeat that? We're talking about the magnitude f plus 9 to the n is less than epsilon squared? I didn't really follow.
This part?
Yes, that part.
This part.
Yes, that part.
So we can take epsilon to be as small as we want. We can dial it to 0. But if we dial that to 0, this is the sum of two positive, these can't cancel, so these each have to go to 0. So F has to go to 0.
Okay, I guess I just slightly wrong.
You're good? Okay. All right. It's the communication through masks. It's crazy.
Is that
Okay.
denim mask, by the way?
No, this is this is actually a vintage material that was imported from Morocco.
Okay.
A friend made it. A friend made these and sold them. But anyway, yeah, it's not denim. But I only wear it with denim because it kind of color matches. Anyway. All right. Shoot. So what was I saying? Go ahead. Yeah, so if Qi forms an orthonormal set or an orthonormal basis for Hilbert space, then that means that any function in Hilbert space is converged. So this is a consequence of what we've just proven, is converged to by Fn of x equals the sum from I equals 1 to n, ai qix. And what's important is that these are constant coefficients. Which means that there is an infinite something where this is a series, not a sequence. Okay, remember the difference between the series and the sequence approximations, because as you do a sequence, then the coefficients can change, but if you're doing a series, then the coefficients earlier in the series remain the same. Okay? All right, now we're going to move past all of this technical crap. Yeah, go ahead.
Sorry, but what does the dot mean over the equals again?
The dot means that this convergence is in the mean. Uniform, so I can't remember the exact details of it. I mean, it's the difference between, I'll grab them for you. Oh my goodness. I shan't be able to find it. Yeah, I'll find it after class. I don't want to delay class anymore. But the conditions for doing it in the mean are looser than uniform or pointwise convergence. And if we're doing it, if we're converging pointwise or uniform, then we'll say that it's equal, but in the mean, we just illustrate with that dot. Okay, so now we're going to get our hands dirty with what you've probably been expecting. We're going to Graham Schmidt And we're going to start to uncover the fruit of all of this labor. Here we go. So I want you to consider, for simplicity, the interval -1 to 1. Okay? And remember everything we talked about with Weierstrass and so forth, we always have to work on a finite interval from A to B, so we're just going to take that interval to be -1 to 1. With an inner product, which is defined, of course, from -1 to 1. The integral of f star g dx. So the weight function in this case is just 1. And what we would like to do, and remember this is a Hilbert space, so these are square integrable functions that we're talking about. But what we'd like to do is we'd like to find a basis, an orthonormal basis, okay? Now we can start with, of course, the basis of polynomials, which is a basis, but it's not orthonormal. But what we're going to do is apply Gram-Schmidt to this to get the orthonormal basis. So you should all know what this looks like. We have our leading contender, p hat 0, which we can just grab the x0 term and use that. Of course, x0 is just 1. So that's 1 over root 2. This, of course, is normalized. To 1. Okay? And then, now, one of the things you might recall is that I actually had you work this out in the homework. You don't have to start with this. You can start with this. You can start with any of them. And then cycle through and now, first of all, if there's an infinite number of them, you should probably start here. Because if you start here, you go to infinity, and then you'll come back and grab these. But there's also this sort of notational thing where the 0th order function that you're trying to generate, you want that to be the maximum order of what's going to be generated in this Gram-Schmidt procedure. So if you want your first term to have an order of no more than 0, you want to pick this one, because if you put this one, it's going to have order 1. Okay? So all we're going to do is we're going to basically pick, to match these indices, the power of these. Okay? Make sense?
Could you give an example?
Well, no, I mean, when I write up what I'm about to write up, it'll be an example. But you just don't want P2 of x to start with x cubed.
Okay.
Okay, you want this number, I mean, this is just a labeling scheme. You can do all kind of various stuff, and depending on what you start with, you'll generate a different set of polynomials. But there is a convention that you match the index on the p, which is just a label. It's just a label, but there's a convention that you match the index of that to the highest order in the polynomial. That's it.
I see.
Okay. And you'll see that on a couple of examples of polynomials that I read up. So P1 hat x. So you guys know how to do this, but I'll just write up one example. I'm sorry, x1. And this comes out to be root 3 over 2, or root 3 over 2 times x. And P2 comes out to be root 5 over 2, 3 halves, x squared minus 1 half. Okay? So as promised, the index labeling the p's corresponds to the highest order in the polynomial. Okay? Now, Graham-Schmitting, it's okay for the first few, but it just gets uglier and uglier the bigger and bigger things get, especially calculating the normalization factor. However, it turns out there is a cleaner way to do this. So it turns out we can actually encapsulate an arbitrary n in the following expression. 2n plus 1 over 2 to the 1/2 is 1 over 2 to the n in factorial dn dxn of x squared minus 1 to the n. Okay? Now let's just see very quickly one example of that reproducing these. Okay? So if I do p2 hat of x, then this is of course 5 halves. Well, it's already starting well. Okay? All right. 1 over 8. And then we've got d2 dx squared of x to the 4th minus 2x squared plus 1. Okay, well, take the second derivative of that, and there you're going to pop it out. Okay. Now, why is this valuable? Well, remember, to Graham-Schmidt it, if I asked you, I would like for you to Graham-Schmidt this and report to me that polynomial. How many do you have to figure out before you figure out P88? 87. Yeah. You got to do 87, and then you can do P88.
Go to 0.
Huh?
Go to 0.
We gotta figure
Oh, sorry, you're right, 88. You got to do 88 in order to get the 88th. I'm saying, I don't know if you can hear me through my mask, okay? But this lets you jump straight to anyone. This is obviously a more powerful, potent way to do it, okay? Now, these right here are really just the normalization factors, okay? So everything to the right of that is really just the numerator. So all of this stuff here is the numerator of each of those. And then that coefficient is just the normalization factor. Now I say that because if I ignored the normalization factor, then, sorry. Then my set of orthogonal polynomials, not orthonormal, but orthogonal polynomials are given by this expression. Does anybody know their name?
Legendre polynomials.
These are the Legendre polynomials. And this shortcut to finding them is called okay, the Rodriguez formula. Okay? Yes?
So how does one find a formula like that? Because it looks like it has a few bits from like the Dirac spike that we're looking at.
So we're not going to derive this one, but we're going to derive one later.
Neat.
Okay? All right, so that's cool,
Yes.
but we can do better. Yeah, we can do better. We can do better than the Rodriguez formula.
Wait.
Huh?
Are they?
Sorry, say
So
again?
Legendre
no. Each of these for a given n is a Legendre polynomial. This process of finding them through this expression is the Rodriguez formula.
Good.
Yeah.
Thanks.
Okay. So, how many of you are aware of the binomial theorem? Yeah, okay. So if we utilize the binomial theorem, then we can actually show, and x squared minus 1 to the n is equal to the sum from m equals 0 to n of n choose m, x to the 2m, minus 1 to the n minus m. And then the Rodriguez formula can be manipulated in the following manner. Where this p is equal to n over 2 for n even, and n plus 1 over 2 for n odd. Okay? The advantage, of course, is that we no longer have to take derivatives. Because, in figuring out the 88th element here, we had to do 88 derivatives. That's kind of tough. Here we don't have to do it. Okay. All right. And I have an example of applying this expression in order to get P2, but I'm not going to go over that now. Okay, so, all right. Now, what the book does is it actually goes through and argues that the Rodriguez formula provides us with a complete orthonormal basis, or actually a complete orthogonal basis. Okay? If you want to call this the Rodriguez formula, then when you can say this Rodriguez formula supplies us with an orthonormal basis. Okay? So what I mean by that is you could start with this expression and using this show that the set of functions which it generates forms an orthonormal basis. Okay? I mean, we came at it from this other approach, but you could just start with this alone. Now, okay, so you're probably aware that the Legendre polynomials were found as the solution to a differential equation. So let's bang out what that differential equation is. So let's start with the identity, x squared minus 1 d x squared minus 1 to the n is equal to 2nx x squared minus 1 to the n, where the d just means derivative with respect to x. Okay? Now, if we want to differentiate each side of this n plus 1 times and use the Leibniz rule, which is then for the left-hand side of this, we're going to get the following expression. So again, I want to take the n plus 1's derivative of both sides of this. They're still going to be equal. And in writing down what that derivative is going to give us, we're going to use a Leibniz rule. So here we go, on the left. You know, normally this is the point where in class and I'm standing here staring at the board writing so much, I ask someone to tell a joke. I'm just saying.
Are you asking?
I'm just saying. Anyway, for the right, I didn't think any of you had any jokes. Okay. Doesn't it seem odd that this is truncated? There are only 3 terms?
What are you asking?
Well, I mean, so how many terms should I get when I use the Leibniz rule when I'm going to n plus 1?
Oh, I would write it all down.
Huh?
You get n terms, right? Or n plus one.
Yeah, but I only got 3 terms.
I like that.
Well, n must be 3,
Yeah, n is equal to 3.
clearly.
N is equal to 3, n is equal to n. N is equal to n.
Is the derivative of that term equal to what we started with? Because the last term is just v, or like the nu v.
All the other terms are 0?
You just got bored of writing, so you stopped.
No.
It's a good enough approximation.
No one told a good enough joke.
So,
If we tell a good joke, can we get the rest of it?
is it that the terms canceled with each other, or is it that a lot of the terms came out to 0 after it?
Well, let me think. DNUV. Oh, wait a minute. I get a U term, I get a derivative of U term, I get a derivative squared U term, I get a derivative. What's next? I get a
Yeah.
D3. But look at what U is.
That's 0 after D3.
Yeah, so it's 0 after the third derivative. Or it's 0 as of the third derivative. Okay? So we have the dku equals 0 for k greater than or equal to 3. That's why it's a finite number of terms. Okay? All right, so like I said, we're taking the derivative of each side of this. So if we subtract them, we should get the same, or the difference should be 0. And so doing that, we're going to get x squared minus 1 d n plus 2 x squared minus 1 to the n, plus 2x d to the n plus 1, x squared minus 1 to the n, minus n times n plus 1, dn, x squared minus 1 to the n equals 0. And now what we can do is we can grab the Rodriguez formula and we can come in here and replace these with the various PNs. Okay, we might have to massage the coefficients, and in the end what we'll get is the following. X squared minus 1, 2 to the n factorial, d2 pnx, plus 2x 2 to the n factorial, dpnx, minus n times n plus 1, 2 to the n factorial, pnx equals 0. Okay. That's literally just taking this expression and using it to replace these derivatives. Okay. Now obviously everything has a factor of 2 to the n factorial, so we can get rid of those. And then what we're left with is 1 minus x squared pn double prime of x minus 2x pn prime of x plus n times n plus 1 pn of x equals 0. And that is Legendre's equation.
Did you just negate it?
Huh? Say it again?
Is the last term, is the last line negative? Like, did you negate it?
Yeah, no, I forgot. Sorry. Oh, no, sorry. Hold on a second. Yeah. So this should be, yeah, that's right. I swapped the order of these. The x squared minus 1 here, I turned into 1 minus x squared, so I multiplied the whole thing through by minus 7.
Yeah, that's what I was asking.
Yeah. Okay.
Why do we set this equal to 0 again?
Huh?
Why do we set this equation equal to 0?
Because we started out with this, but the difference of this should be 0. This minus this should be 0. I took the n plus 1 derivative of each side, but the difference in those should be 0. So when I started setting things equal to 0, it was taking the difference.
Okay.
Yeah. I mean, it's,
That makes sense.
if you prefer, here.
No, it's okay. Thank you.
That's also the Legendre equation, just in case you're biased. Okay. Actually, it's interesting. That is going to be the form in which we will cast it later on. So I'm not screwing around with you. That is the same equation. And it's that in that form, it's going to be important later on. Okay. How we doing? Legendre good? Legendre bad? Legendre sucks? Okay. Well, we're going to swap gears. I can't hear what y'all are saying, and I don't think I want to.
It's just a joke.
Okay, all right. Well, I know you're telling jokes. You're supposed to be telling jokes while I'm writing on the board.
Yeah,
for
but you wouldn't
lengthy
get it.
expressions and
Yeah. Past your time. Not for fools.
Okay, so now I am going to change this. Are you ready? Here we go. Let us make our interval a little bit bigger. Because after all, 1 is such a special number. It's the identity. You know, it kind of sucks. So we want to just take that and make it a little bit bigger and see what the differences come into play when you're not dealing with the number 1. Okay? So we're going to expand our range just a little bit. by making it infinite.
Okay, all right.
Why not? No, I'm just kidding. It's not that one is important. One is not important at all. A, B, remember that can be mapped into any range you want, but infinity is a very special thing. So what we would like to do is we would like to explore a complete orthonormal set of functions
Are we changing the
Of-
integral too?
Say it again?
Are we changing the bounds of our integral too with this?
Well, hold on. So I'm about to address the inner product, but I want to find a complete orthonormal set of polynomial functions, okay, over the range from minus infinity to infinity. Of course, that stands in the redefinition of the inner product, but what is the problem?
Well, that's gonna be infinity for polynomials.
Exactly. Polynomials
Well, where could I expect you to
do
see
not
that?
go to 0 when x goes to infinity.
Technically, that integral come out to 0, I guess, right?
It should.
It could.
Well, let's see.
Oh, that's good.
What do you think?
That's gonna be infinity.
Okay, all right. So, yeah, What can we do? Yes?
Well, I just want to voice my concern that I don't like the fact that the set notation is the same as the inner product notation.
Yeah, and I realized, yeah, okay. So we'll just have a quick discussion and I'll adopt his notation in the book. Normally, whenever you've got infinity in your set, the actual value of infinity is not included, okay? It's not a closed set if you're going to infinity. So in the book, he does this. Sorry, minus. In the book, he does this in the same notation that he does with all of his other intervals, because this is degenerate with the inner product, okay? So I'll just do the square brackets, but you just have to be aware that this interval does not actually include the values of infinity and minus infinity, okay? And if I accidentally write up Kirby's, if I write them around minus infinity to infinity, I hope you realize I'm not taking the inner product of those, but just in case. Okay, so here we go. Now, this is clearly diverging. How can we fix it?
Divide by 0.
Divide it by 0. That's it. Let's go. Go home. No, I'm just kidding. Yeah, no, we won't divide it by 0. Because this is infinity times infinity, which is infinity squared. We want to multiply it by 0. Actually, we do want to multiply it by 0. Well,
Multiply it by something very close to 0.
do we want to multiply it by 0 everywhere?
Oh, no. Just outside of 1 and minus
Only a
1.
big number.
Only big numbers. How can we do that?
Weighting function?
A weight function. Remember, in defining our inner product, we were always given the freedom of introducing a weighting function. The weight function is part of the definition of the inner product. So it doesn't matter what f and g you put in here. You can pick any f and g you want. You always use the same weight function. So this is a part of this definition for any f and g. Okay? Now you can certainly imagine a weight function which would take care of the infinite divergences, but the one that we want to pick on is e to the minus x squared. Okay? All right. Now, with this in mind, let's Graham-Schmidt it. Okay, we're going to Graham-Schmidt the basic polynomial basis. So if I Graham-Schmidt it, 1 over pi to the 1/4, just so that you see this is normalized. might, at this point, be good for you to brush up on some of your exponential integrals. Okay? So then H1, H1, it turns out, is just x over the magnitude of x, which is equal to root 2 over pi to the 1/4 times x. Okay? And obviously there's more to the Gram-Schmidt story, but I'm cutting corners. It's written up in the notes, but H2 which ends up being x squared minus 1/2 over the magnitude of x squared minus 1/2, comes out to be root 2 over pi to the 1/4 x squared minus 1/2. Okay? Remember, in this one, you've got x minus the inner product of you've got x minus h0 times the inner product of h0 with x, but it turns out that the inner product of h0 with x is already 0. So this is already orthonormal to x, so that subtraction ends up being 0. That's why this simplifies so much. Okay. We can Rodriguez this again. And what we find is the following. All right. Where if we utilize this formula, to find those expressions, what we get is h0x ends up being 1. h1 of x ends up being 2x. h2 of x is equal to minus 2 plus 4x squared. So this just tells you what your normalization factors are. That is 1 over n times these gives you an orthonormal basis. Say it again?
Where did the ends come from? Just from the Gram-Schmidt process, or
Yeah, they're the same ones here.
the ends?
The ends.
Okay.
Oh, no, oh, sorry, the big ends.
Yeah.
Yeah, no. So notice the difference between this form and this form.
Oh,
This one is not normalized.
gotcha.
Don't get me wrong, you might look at one and go, one's normalized. I mean, one is always normal. I mean, what's the length of one? It's 1. Not with this inner product.
Oh.
Okay? Turns out that to normalize it, you've got to pop in this 1 over pi to the 1/4. Here's the argument why. Okay? Okay, thanks. Now, are these complete? Okay, you can Gram-Schmidt the thing, but then there is the open question, is the resulting set complete? Well, for the Legendre polynomials, we actually utilize the argument due to Weierstrass to argue that that would be a complete set. Okay? However, the argument due to Weierstrass is restricted to finite intervals. This is not a finite interval. Okay? Yes?
Could we like take a limit?
No. No. I mean, Weierstrass actually uses the endpoints of the interval as part of the analysis.
Oh.
You can't just grab the endpoints because they're not included in this set. Yeah. Okay? Well, it turns out that you can prove that these form a complete set, but they utilize techniques beyond what we want to do. So we're just going to accept that these are forming a complete set. And they have a name. What are they called? The Hermite.
Hermitian.
Hermite Hermite polynomials.
Hermite.
You guys are screwing with polys. Okay? Now, again, we did the same thing we did with the Legendres. We got their normalized versions. We got a Rodriguez formula. That gave us the unnormalized versions. Okay? We proved completeness in the Legendre case. This case, we're going to skip it. All right? What's the last thing we did for the Legendre case?
Differentiate both sides.
Well, we were doing that in order to find what? The differential equation to which the Legendre polynomials are solutions. That was the point of that analysis, is you want to find a second order differential equation that the Legendre polynomials were solutions for. It's kind of weird, right? Because normally you're given a differential equation and then you go and solve for the solutions. This is backwards. We start with a set of solutions and we want to find the differential equation. And that's why we did that little analysis of taking plus one derivatives. So we're going to redo that for the Hermite polynomials. Yes?
Real fast, I'm a little behind on the weight thing of the inner product.
Yes.
Do you have to do any, like, is that always allowed to just add a weight function?
Yes, in fact, when I do my more general discussion next time, that's going to be a very important part of the story, is the weight functions.
Okay.
And we're actually going to look at them in general next time, and we're going to find certain conditions on them.
Is it allowed if it's a finite inner product to just slap a weight on it?
You can, well, you can actually slap, in defining your inner product, you can slap anything you want into it in terms of a weight. We will be working in a particular paradigm called the Sturm-Liouville paradigm. And that is going to require certain constraints on the weight functions, but you'll still have a myriad of possible weight functions. But if you're not trying to stick to a certain class of systems, you can put anything you want in there. I mean, normally you want the result to be finite, so something which dies off. Okay? And the good thing about this is that this dies off faster than any polynomial grows. That's why we're using an exponential. I mean, you might have wondered, why not use 1 over x? Well, if you got 1 over x in here as your weight function, this is definitely going to 0 as x goes to infinity, right? But if your polynomial is that, you're screwed. However, e to the minus x squared goes to 0 faster than any polynomial blows up. Yes?
Why do we care about the differential equation?
I don't. I mean, screw it. Let's go home. No. So in all seriousness, in our unification argument next Tuesday, the differential equation will be the seat of it. Okay? I mean, so it's kind of interesting because, for example, if we pick the interval from -1 to 1, and we pick the weight function to be 1, it turns out that this uniquely leads to the Legendre functions as an orthonormal basis. So there is a certain sense in which the interval over which you're working and the weight function with which you're working corresponds to a particular set of functions. There's no freedom there. And they will satisfy differential equations. But you could turn this analysis around and say, let me start with a differential equation which has got some degrees of freedom in it. I mean, this is the one that was down here was very well defined differential equation, but we could imagine starting out with a differential equation with various parameters that we could tweak, and from that differential equation, depending on the values that those parameters take, we might find the Legendre polynomials as a solution. We might find the Hermite polynomials as a solution. So all of a sudden, all of these functions, all of these polynomial sets are the result of solving this one differential equation. So it's the differential equation that's going to unite them.
Pretty cool.
Okay, we'll talk about that next Tuesday. At any rate, what I want to do now is I want to get the differential equation that these Hermite polynomials satisfy, and this is going to look a little bit different than what we did for the Legendre case, as you might expect. So what I want you to do is, yeah, we'll get rid of these. Okay. So first of all, what I want to point out is that for the Hermite case, there is this thing called a generating functional. Oh, sorry. I'm looking at different points on the paper. I don't want to do that. Okay? And from this generating functional, or from this generating function, you can actually derive the Rodriguez formula for Hermite polynomials. Okay? Now we're not going to do that. We're rather going to use this generating functional to derive the equation of motion satisfied by the Hermite polynomials. But in the book, this is how they derive the Rodriguez formula. So what I want you to realize is the following. First of all, if I take the derivative of this with respect to x, I get 2x e to the x squared e to the minus t minus x squared plus 2t minus x e to the x squared e to the minus t minus x squared. Hold on. Oh, wait a minute. This and this do what? They cancel. All I'm left with is 2t times this, which is what I started with. Okay? But that tells me that the sum from n equals 0 to infinity of hn prime x over n factorial t to the n is equal to the sum from n equals 0 to infinity of 2 times hn of x over n factorial t to the n plus 1. All I did was I took this and I multiplied it by 2 and t, which raised the power of t. Am I on board? Okay? All right. Now, let's take d phi dt. You take d by dt, t is sitting in the exponent, all by itself, so clearly you're going to get something like this. And then this immediately tells us that the sum from n equals 0 to infinity of hn x over n minus 1 factorial t to the n minus 1 is equal to minus 2. Sum from n equals 0 to infinity hn x over n factorial t to the n plus 1 plus 2x sum from n equals 0 to infinity hn x over n factorial t to the n. Okay, well, let's take this guy. This is the equivalence of two sums, but they're sums over this t to the n. So that means that the term on the left that corresponds to the t squared term has got to be equal to the term on the right, which has got t squared in it. Okay? So we can go through here and equate the left and right side for each power of the t. All right? If we do that, then in this case what we determine is that hn prime of x is n factorial over n minus 1 factorial 2 times hn minus 1 of x, which is just 2n hn minus 1 x. Okay? I mean, if I'm going to use t to the n here, I need to be using t to the n over here, which means I need to be using the n minus 1, so that when I plug in n minus 1 for n, I get t to the n. All right? And then I just took the factorial here, put it up here, and then I just used that n factorial is n times n minus 1 factorial to cancel it out. Okay? Similarly, from here, we get an expression equating the powers of t. Which gives you 2n hn minus 1x plus 2x hnx. Okay? Now I'm going to call this recursion relation number 1. And I'm going to call this recursion relation number 2. All right?
Is the first term and the second one, is that hn minus 1?
Yes.
Yeah.
Now, what we would like is an equation which only involves a single n. Okay, I mean, these recursion relations are sort of mixing up n's and then minus 1's. What we would like is we would like an equation for hn. Okay? So what we can do is we can combine those two recursion relations, and we get the following. This is recursion relation number 2. Okay. And then I can say the following. hnx minus 2x hn minus 1x plus 2 times n minus 1 hn minus 2x equals 0. That's just this recursion relation dropping n to n minus 1. Okay? If I see to go from here to here, I just took n everywhere in here and dropped it to n minus 1. It's still going to be true. Okay? And now what I can do is I can say, all right, hn minus 1 is hn prime with that coefficient. So I can take this hn minus 1 and I can replace it with h prime n x over 2n. And then I can take this hn minus 2 and replace it with hn minus 1 prime over 2 times n minus 1. which of course is just h n primed of x over 2n totally primed to n minus 1, which is just the second derivative. Okay, sure. All right, well, I got one more line to write down. Okay? So in the end, this is going to give us, notice, hn, hn prime, hn double prime. That's what we want. So we're going to have hn of x minus 2x over 2n, hn prime of x plus 1 over 2n, hn double prime of x equals 0, which is just begging us to multiply through by 2n. There you have it. This is the Hermite equation. And you might notice, once again, it's a second order differential equation. If you solve this, then the solutions are the Hermite polynomials. Now in the title to this lecture, I put Laguerre. How many of you heard of Laguerre? How many of you are excited that in your homework you're going to do all this for the Laguerre? Joel's excited. All right, that's it. You are going to get this in your homework. That's why I did 2 examples today, but I'm going to ask you to repeat this for Laguerre. Laguerre is going to use a different interval and a different weight. Okay? But you're basically going to follow the exact same steps that I did. I won't ask you to do everything, but a few important steps. All right. I'll see you guys on Tuesday.